now going to turn our attention to momentum. And momentum is similar in nature to energy, but it's a little bit different. It's really only referring to the moving inertia of something. And so we're going to talk about that and talk about how it kind of the idea of it, how it came about, and then we're going to talk about how to calculate it. We're also going to talk about the factors that cause it to change. So momentum is really a measure of the moving inertia of a mass. So let's just remember what inertia is. Inertia is a tendency for an object to stay at rest or to keep moving at a constant speed. And that was first described by Galileo. And momentum is actually the first thing that Newton talked about when he introduced his three laws. He said, hey, we know that when something's at rest, its inertia is really directly related to its mass. But what about when it's moving? And the first thing he did is he defined the moving inertia of something. He said if something's moving, it has inertia because of its mass and its velocity. So the symbol for momentum is a P, and it is a vector. So if you have a momentum, you have a momentum in a certain direction because it's directly related to the velocity of the object. So if you're moving to the north, then your momentum's to the north, which means that in order to stop your momentum, to change your momentum, you'd have to apply a force in the opposite direction, to the south. It is related to the mass, so the bigger an object has, the more mass, but it's also related to the velocity of it. So if the object is moving 100 miles per hour to the north, and it's only 1 gram, or a couple grams like a bullet, it can have a lot of momentum, a lot of tendency to keep moving. That's why you don't want to stand in front of a moving bullet. But on the other side of it, it could be moving very, very slow, but have a huge mass like that of an 18-wheeler. You wouldn't want to stand in front of that, even if it was just slowly moving, right? Because you wouldn't be able to stop it. It has a large moving momentum. Its units are going to be kilograms times meters per second, which look a lot like the units of kinetic energy, meters squared over second squared. But because it's a meter per second, it is not a joule, okay? It has to be meters squared over second squared to be considered a joule. So we don't really have a name for this unit. It's just kilograms meters per second. So there's no a kilogram meter per second squared is a Newton, and a kilogram meter squared over second squared is a joule. We don't have anything like that for this unit. So can a bullet have just as momentum as an 18-wheeler? Heck yeah. Because if the momentum of the bullet is equal to the momentum of the truck, it has a little teeny mass, but a huge velocity. And the truck, on the other hand, has a huge mass and a little teeny velocity. So, yes, they can have the same value for momentum, right? They can be just as dangerous, just as hard to stop or to get started. So how do you change the momentum of an object? Well, Newton said, okay, you have to apply a force, but the amount of time that you apply the force is really important. And he came up with a new term called impulse. You have to apply an impulse to it. And the symbol for impulse is J, and it is in fact equal to the change in momentum. It's also equal to the force that you apply to it times the time that it's applied for. So it's equal to both of these. And that means that we have a new theorem. It's called the change in momentum impulse theorem. Remember, we had the work kinetic energy theorem. Now we have the change momentum impulse. So F times delta T is equal to PF, which is mVF minus mVI. So let's do an example. So if we accelerate a ball from 3 seconds to 20 meters per second, and we want to find the momentum. First of all, let's give it a mass. We got to have a mass for it. So 1 kilogram mass. For 3 seconds, we can find its change in momentum, right? Its change in momentum is its final momentum minus its initial momentum. Well, it started from rest, and it left our hands at 20 meters per second. So the change in momentum would be 1 kilogram times 20 meters per second minus 1 kilogram times 0, which is 0. So the change in momentum would simply be 20 kilograms meters per second. If we want to know the impulse delivered to it, it's equal to the change in momentum, which is 20 kilograms meters per second. So what does this mean? It means that there was a force delivered to it. So if we wanted to find the force applied to it, we either would need to find its change in kinetic energy and know the distance and use the work energy theorem. But what we have the time that it's applied. It's applied for 3 seconds. So if I take this formula here, F equals the change in momentum all over the change in time. Well, I have the change in momentum, or the impulse all over the time, right? It's the same, they're the same thing. So I've got that. So the force in this case would be 20 kilograms meters per second divided by 3 seconds, which is 6.67 kilograms meters per second squared, or newtons. So the average would have been 6.67 newtons. Now, old school, we would have had to know the acceleration. We could have found the acceleration and then multiplied it by the mass. Could have done that. But we can also use this. So how are they related? Obviously, we can use this formula and that formula. So let's just talk about that. And we'll talk about that in a minute. Let's also talk about impulse in terms of how you know when something requires more impulse. So let's just take an example of a ball that just lands on the ground. So the ball falls and then it just stops. So it has some initial speed and then its final velocity is 0. So it just lands on the ground. Versus it has some initial speed and it bounces up with some speed. Which one has a bigger impulse? Well, impulse is either F times T or the change in momentum. Can't really look at F times T here, but we can look at the change in momentum, right? So the more impulse means the more change in momentum. So let's talk about that. Let's do some numbers. Let's say that it starts out at 10 meters per second here and goes to 0. And it starts at 10 meters per second here, and then it bounces back at negative 10 meters per second. And let's say that it's a 1 kilogram ball. So if we were looking at scenario A, just landing, then the change in momentum would be 0 minus 1 kilogram times 10 meters. Meters per second, which would be negative 10 kilograms meters per second. So it loses 10 meters per second, or it changes its velocity in the opposite direction. For the bounce, J would be equal to the final minus the initial. And the final would be 1 kilogram times negative 10 meters per second minus the initial, which would be 1 kilogram times 10 meters per second. So I've got negative 10 plus a negative 10. I would have negative 20 kilograms meters per second. So this has more of a change in momentum or more impulse. So the bounce is the one that has the biggest impulse because there's more change in momentum. Just think about it. One stops, but one actually stops and turns around and gains speed in the up direction. That's a huge change in momentum. So how is force related to this? Well, force is change in momentum over time. How do I know that? Well, I know that force times time equals change in momentum. This is actually change in time, right? It's the time over which the force is delivered. And if I solve for force, it is equal to delta P all over delta T, which means that it's the rate that momentum changes. So impulse is the change in momentum, but force is the rate that it changes at. Is this related to our F equals ma equation? Yes, it is. So let's take a look at that. If I solve for force here, right? Change in momentum is mvf minus mvi all over our change in time. Let's kind of take out our common thing here. This would be m times vf minus vi, still divided by delta t. Notice that this is acceleration. So really this is the acceleration formula. When Newton came up with Newton's second law, this is how he derived it. He derived it in this way. He defined force, that push that causes that push or pull or outside action that causes a change in momentum, as the rate of change in momentum. So the average force exerted on that baseball, on the baseball player in the previous problem that we did. So let's go look at that. So we had, we looked at it, was the rate at which the momentum was changed. The momentum change was 20 kilograms meters per second divided by 3 seconds, which gave us 6.67 newtons. So one thing to note is that the force in the time over which it's delivered is inversely proportional. So F equals delta P all over delta T. F is inversely proportional to time. So that means that the shorter the time the force is delivered, the more force is required. So think about a glass falling on a hard floor versus a carpet. So both of those, in both of those examples, whether it falls on a cement floor or a carpet, you're going to have the same change in momentum, right? Maybe you're going to go from 10 meters per second to 0. The difference is that the carpet has a larger amount of time because of the cushion that it provides, which means that it requires less force for that change to occur versus the cement floor, which has a shorter amount of time and a larger force. So it's much more likely that that glass will fall. Think about a baseball player and how they catch a ball. When they catch the ball, they don't hold their hand out rigidly. They actually catch it and move back with the ball as it comes to a stop. That, in effect, cushions it. When they move with the ball, they are increasing the amount of time over which the force is delivered, which reduces the amount of force to change the momentum of the ball. And they don't break their hand. Also, the mitt helps with that as well. But if they were rigid and they caught it, the amount of time that required to make it stop would be very short, and it would require a lot of force. Because of Newton's third law, it would hurt. So let's do another example. A ball is thrown at a speed of 20 meters per second. What is this change in momentum? Well, it starts out at 0 and it ends with 20 meters per second. So it's change in momentum is mvf minus mvi. Vi is 0, so this will be 0. So its change in momentum is simply 1 kilogram times 20 meters per second, or 20 kilograms meters per second. What is the impulse delivered to it? Well, that's simple. Impulse is equal to delta P, so it is also 20 kilograms meters per second. It's accelerated for 1 second. How much force is applied to it? Well, force is the rate at which the change of momentum happens. Well, that's 20 kilograms meters per second divided by 1 second. So that's 20 newtons of force. That easy. Let's do another example. A ball hits the floor with an impact speed of 10 meters per second, and it bounces up with velocity of 10 meters per second. So it goes down like this and it bounces up. So I'm going to say that it hits with positive 10 meters, but since it's bouncing up at negative 10 meters per second. You could switch it around if you want to. You could say negative 10 and positive 10, but they've got to have, because they're vectors, they've got to have the directions associated with them. The impulse is going to be the change in momentum, and let's just use that 1 kilogram ball again. So the final momentum minus the initial momentum is going to be 1 kilogram times negative 10 meters per second minus 1 kilogram times positive 10 meters per second. So J is going to be negative 20 kilograms meters per second. If the ball is in contact for 3 milliseconds, what is the force delivered to it? It is equal to the change in momentum all over time, or J all over time. So negative 20 kilograms meters per second divided by milli. 3e to the negative 3 is 0.003 seconds. So 20 divided by it is going to be negative 667 newtons. Now it's negative because it turns around. The force has to be acting in the up direction in order to make the ball turn around. All right, let's take a bullet problem. What is the average force exerted on a bullet that's accelerated to a speed of 60 meters per second in 20 milliseconds? Well, force is change of momentum all over change in time. It started at 0 and it left at 60 meters per second. And the mass is 0.03 and the time is 2.00 e to negative 3 seconds because it's milli. So I'm just going to plug this in now. The mass is 0.03 kilograms times the final, which is 60 meters per second, minus the initial, which is just going to be 0, all over 2 milliseconds, 0.002 seconds. So 0.03 times 60 divided by 0.002 is 900 newtons. So once again, if we had done this problem before, if we were doing this with energy conservation or work energy theorem, we would have to know the distance. But when you're given time, you should be using the equation that has time in it versus an equation that doesn't have time in it. All right, let's take another example. So one of the hazards of space travel is debris. So imagine that you have very small objects, flakes of paint, that are 0.1 milligrams. So the mass is 0.1 milligrams, or 0.1 thousandths of a gram, which is 0.0001 grams. And they're going to hit with a relative speed of 4 times 10 e to the 3. So they're going to hit with an initial speed of 4,000 meters per second. They're going to come to a stop when they, hit the glass. And they're going to do that in 6e to the 8 seconds. Let's find the force. So force is going to be equal to the change in momentum all over the change in time. And this is PF minus PI all over time. PF is going to be 0. PI is going to be 0.000, that should be so let's change this to kilograms. So 0.0001 grams, and there's 1,000 grams in a kilogram. So this is going to be 0.0000001 kilograms, or 1e to the negative 7 kilograms. So this is going to be 1e to negative 7 kilograms times 4,000 meters per second, and it's going to be a negative number, divided by 6e to the negative 8 seconds. So let's do this. Okay, so we're going to have to make sure we're using our exponents correctly. So if I do that, I'm going to put in, and let's make sure we have this where I can see it, 1e, 1 exponent, negative 7. Oops, let me clear that. 1 exponent, negative 7 times 4,000 equals, divided by 6 exponent, negative 8 equals. And that's going to give me a force of, what was that number again? 1.67 times 10 to the 7. 1.67 e to the 7 newtons. Now it's negative, right? Because we were subtracting that off. Now, let me remind you, that's a lot of force, right? That's a huge amount of force. And that's why we have to be worried about those types of things out in space, especially if we are talking about a space shuttle or people out there. And that's momentum.